Hi everyone, I am Rishabh. I'm a researcher at Google Brain in Montreal, and I guess I'm going to talk about our recent work on reincarnating reinforcement learning. Before I start, one clarification. I'm not saying reinforcement learning is dead. I'll explain what reincarnating RL is, and I think hopefully you'll understand what I'm trying to argue for here. Cool. And you can find more details at the website link below. This work is done with, I think, some people at Google and Mila, including Max, Pablo, Aaron Dorville at Mila, and Mark Belmel. Okay, so I guess what I want to say is like reinforcement learning is a general purpose area for solving decision-making problems. And because of this generality, the prevailing trend in reinforcement learning research is to learn agents or systems that can operate without much previously learned knowledge about the problem, including, let's say, knowledge could be in form of, let's say, data sets or previous policies you learned, or so on and so forth. Basically, we still train RL agents from scratch most of the times. Now, this works pretty well if you think about a research domain, such as, let's say, what Rosine was mentioning, Atari or Mojoko. But if you look at like large-scale problems, such as, let's say, playing Dota 2, or things like, let's say, solving Rubik's Cube, tabula rasa RL systems are more like the exception rather than the norm for solving such large-scale problems. And I guess one reason is that if you want to restart such large-scale RL systems from scratch so that you can incorporate any system or design changes, such as, let's say, your environment changes, or you want to add some sort of algorithmic change in your agent, it might require weeks or even months of computation. And there might be even billions of data points to reprocess. And this might make the tabula rasa approach impractical. So let me just give you like actual examples of this. So the system which OpenAI trained to play Dota 2 at a human-like level, this system was trained for around 10 months. And with continual changes in things like model architecture, environment, and other things during its development. And now this required building upon the previously trained system after each such change so that they can circumvent retraining from scratch. And this was done using an ad hoc approach called model surgery. So here, I guess what I'm showing on the slide is if, let's say, after each change, so they had to do around, I think, 15 to 16 changes. And after each such change in, let's say, architecture or environment, if they were to restart from scratch, the project would have taken actually 4 years, but it actually took 10 months because the OpenAI folks were smart about, okay, I have trained an agent for 2 months. I don't want to throw it away. I want to build on this somehow and introduce the change I want to make. So that's example one. I guess the second example again is from OpenAI. So I don't know if you remember this, but basically there was another work from the same OpenAI team about like basically manipulating a Rubik's Cube using a robotic hand. And this also underwent several months of reinforcement learning training with continual changes during its development. Now, I'm just taking some quotes from the paper, which is they say, oh, we rarely trained experiments from scratch, or restarting training from an uninitialized model would have caused us to lose weeks or months of training progress. So again, here, let's say you have an agent architecture or something, and you want to go to a bigger architecture, or let's introduce some other sort of change. Rather than just now restarting training from scratch, these guys used actually distillation. So they converted one policy to another and then trained that policy further to avoid losing months or even weeks of progress. I guess the other, or also there's a lot of prior work which also focus on fine-tuning existing agents with deep RL so that they can reduce training time and sample complexity as opposed to training from scratch, especially on real-world problems such as, let's say, chip floor planning work from Google, or robotic manipulation, and even things like compiler optimization. So you can see that at least in a lot of real-world setups, when RL is applied, you don't really train RL from scratch. You focus on reusing what you can, and I guess often fine-tuning RL agents. Now, that's one setup. The other issue with, I think, current setup or current tabula rasa RL paradigm is that it is computationally expensive. And if you want to tackle challenging problems with deep reinforcement learning, it often incurs substantial computational and financial cost. I'm just giving you one example here. So AlphaStar, which was trained by, I think, DeepMind, achieved Grandmaster level in StarCraft. And it was trained on TPUs for around, I think, 500 TPU days. And if you just want to replicate the final agent, it will cost you around several $1 million. And as a result, the majority of the RL community outside these resource-rich labs is currently excluded from tackling such problems. So you might argue, well, we really are not training StarCraft agents for research because maybe it's too large scale. So let's just come to our more standard benchmarks like Atari. So even thinking of Atari, if you want to, let's say, train 5 runs or 5 seeds on 50 plus Atari games for 200 million frames, which is the standard protocol, this requires at least 1,000 plus GPU days. Again, so this would exclude most researchers outside resource-rich labs, like including my own. So basically, majority of the community in reinforcement learning is not able to tackle even the standard benchmarks we have here. So there are two problems with tabula rasa. One, it doesn't really match what we often do in practice, because when we have to solve large-scale problems, we can't really use tabula rasa. The other is, because of its computational cost, most researchers are not able to tackle challenging problems. Now, this is, I think, the pitch of this talk, more or less, which is, well, what if we didn't always train RL agents from scratch, even when we are doing research? Hopefully, so far so good. No questions. Okay, so what I was saying here, so what I was saying, like, to address both the sort of sample and computational inefficiency of tabula rasa RL and help unlock the full potential of deep reinforcement learning, in this work, we're presenting reincarnating reinforcement learning as an alternative research workflow or way of doing things. You can also think of it as an alternative class of problem settings. Now, what's the setup? So reincarnating reinforcement learning is based on the premise of maximally leveraging existing computational work, such as, let's say, learned network weights, collected data, learned policies, and so on, to accelerate training across design iterations of an RL agent, or when moving from one agent to another. So in this sort of workflow, agents need not be trained tabula rasa, except when you're really going into a totally new problem and you're trying to do some initial effort. So maybe this will be clarified in this slide. So let's say you're a researcher and you train an agent for a long time, maybe it's few days, weeks, months, I don't know. And now you want to experiment with better architectures or algorithms. Now, the current tabula rasa workflow is, well, you just train another agent from scratch for like maybe the same amount of time, which will be days, weeks, or months. In reincarnating RL, you get two additional options, which is you can fine-tune the existing agent, but it's kind of restricted because you have to use the same agent and maybe the same architecture, or you can transfer this existing agent to another agent and train that agent further. So feel free to train the agent from scratch, but let's say you have finite amount of compute, maybe like one of these two other options would be much more viable to, like, let's say, experiment with these better algorithms and architectures. Hopefully people understand what this is. So why even bother with this sort of workflow? So I guess the one argument is, and I think this should be easy to understand, which is as we make research progress, things like better algorithms or architectures, improving existing RL systems would require incorporating some of these developments. And this sort of workflow of reincarnating RL would allow us to do so viably as opposed to retraining from scratch. And I think I also put a cheeky meme on the slide here that how tabula rasa RL can be very expensive.
So this is the same as what you described the open air work we're doing, right?
Sorry, maybe I didn't understand the question.
Oh, the question is, in the beginning, you showed the Rubik's Cube and what's the other one, Yoda. So do you consider them doing reincarnating RL?
Yeah, they are doing it. I guess I'll talk about them again. So they are doing it. They are doing it in a very specific context and way. So you can't do it for all projects, but they are doing reincarnating RL in a specific way. Okay. Like, so for example, I consider fine tuning also as reincarnation because you're focusing on reusing an existing agent, but it's very limited because you can't try out a lot of new things with fine tuning. Okay. So I guess my slides are deleted somehow. But anyways, I guess the other point which I also mentioned before was you can tackle more challenging problems without having excessive computational resources if we are willing to build on prior computational work. So let's say I'm at Google, I release some sort of agents which are trained for a week or something, and now researchers outside Google can maybe pick up this agent and use this agent for further research using only a few hours of compute, as opposed to training another agent for a week. I guess one fun thing which could happen if this sort of paradigm is adopted is now researchers can actually continually improve and update existing trained agents, especially on problems where improving performance has some sort of real world impact. So for example, think about problems like, I guess these are the recent real world RL applications or sort of projects you might have seen, which is controlling like nuclear fusion plants or balloon navigation or even chip design. In this sort of project, maybe you can take an existing agent and try to improve on it, as opposed to beat this existing agent by starting from scratch. And it would also have some sort of real world impact if we do this. And finally, I guess reincarnating RL as a paradigm is pretty suitable for real-world application because prior computation is often available. For example, think of a setup where you already have some sort of deployed policy or something is already deployed and you want to use RL. Possibly, rather than throwing away this deployed policy, you would want to build on the top of this policy because it doesn't really make much sense that you will just throw away whatever you have done so far in the last few years, and then you'll just say, okay, I'll just redo everything from scratch. Okay. I guess I can skip this slide. Coming back to Roseanne's question. So ad hoc reincarnation strategies are actually common in large-scale RL papers, or let's say if you see like Nature publications. But reincarnating RL is actually pretty rare in typical research papers at conferences such as, let's say, ICLR or NeurIPS. And I can just quickly describe what are the ad hoc strategies people have used before. So Dota 2 use something called model surgery, where you can go from one architecture to a slightly bigger architecture, but it's limited because, for example, you can't make all sort of architectural changes. So you can't go from a big architecture to a small architecture, or you can't introduce, let's say, LSTMs or transformers into an MLP. Rubik's Cube use something called policy distillation. So you can't go from, so you can go from one policy to another policy, but you can't use like policy to Q values and stuff like that. AlphaGo fine-tuned an existing agent, and same this Minecraft VPT work, I think, which was presented some time ago in this, or at least there was some sort of panel discussion. So they also fine-tune an existing policy with RL, but then with fine-tuning, you're restricted to the same architecture. And AlphaStar use population-based training. Again, you have to use the same architecture when you're doing something like that. But basically, there have been strategies which you can use, but there's not been really that much focus on this sort of problem as a research problem in its own right. And this is what this work is arguing for, that, hey, this is not really a problem just for large-scale applications. Maybe we should also do research on this important problem. I hope this is good. And I guess maybe this is a slide which I presented earlier. But yeah, this work is simply arguing that this doesn't really have to be the case, that we can also study or develop general purpose reincarnating RL approaches as opposed to ad hoc solutions. All right. And I guess maybe one clarification I want to give is, so how is this different from what has been done before? Stuff like, let's say, combining imitation learning plus reinforcement learning, offline RL, transfer, LFT, and so on and so forth. So I guess one difference is that most of these areas don't really focus on incorporating method, or at least incorporating prior computation as part of how we do RL research itself, which is they're not trying to change how we do research. They are trying to leverage prior computation, but not really trying to change how our average researchers does things. For example, and as such, we still largely train, let's say, Atari agents from scratch, but that doesn't really make sense. Like, why are we training agents again and again to solve the same part of the games or solve the same levels of a given game? Why not build on top of these or top of existing progress? Now, reincarnating RL actually is a pretty broad sort of area in some sense, because you can leverage different ways of representing previously learned knowledge. It could be learned policies, it could be collected data, it could be pre-trained representations, it could be learned dynamics models, and it could be even other things like, let's say, large language models or learned skills and so on and so forth. Now, this is too broad for a single paper, obviously. So what we did in this work was like, well, prior large-scale efforts have mostly focused on the narrow setting of policy-based reincarnation RL, which is you're given an existing policy and you want to, let's say, reuse this existing policy for learning another policy. Here we said, okay, let's just make it like, let's study like a slightly different problem, which is how can we, given an existing policy, how can we transfer it to a value-based agent? I'll clarify what all this means. But basically, the premise is that it's not really clear how to design reincarnating RL approaches that can be incorporated in any RL research project, because we don't really know how to incorporate prior computation in a lot of different forms, except maybe very specific forms. And in this work, we said, okay, let's just study one specific such case to argue for, okay, what are the challenges in this sort of setting, and what can we do if we have that? So I guess this is slide speed. What is happening? Okay. Now, this is the setup for the case study we do in this work, which is we focus on the setting of policy to value reincarnating RL, which is, what is the setup? So I gave you an existing suboptimal teacher policy, and we want to focus on transferring this existing policy to a value-based student agent, which are presumably more sample efficient. So you have a policy, and I want to transfer it to a value-based agent. So the policy could be given to you by anyone. It could be handed to you by God, or it could be your friend who just gave you this policy. And the value-based agent could be anything from like SAC, TQN, depending on whatever your favorite value-based agent is. I don't care. So what are the sort of properties we expect a useful reincarnation algorithm would have? So the first property we said was, well, it should be teacher agnostic, which is the student agent, which we are trying to reincarnate. It should not be constrained by the architecture of my teacher policy or algorithm. Because if that's the case, then there's a limited utility of this, which is, let's say I gave you a teacher policy and you have to use the same architecture. It is very limiting. So we want researchers to reuse this policy and do very creative things. And we're saying, well, let's not limit ourselves by what was the algorithm used by the teacher policy or the architecture. So the algorithm should be teacher agnostic. Second property, I guess this is probably the most important one, which is we want to wean off the dependence on the teacher, which is as we learn, we want to wean off this teacher, because let's say you want to do reincarnations multiple times over the course of a project, or from one project to another. It'll be really annoying if you have to keep track of all the previous teacher policies and like have them. So let's say I did reincarnation from some existing policy, and then Roseanne picked my agent and tried to reincarnate, and then let's say someone else do it again. So now here they have 3 teachers if we don't wean off this teacher dependence. It'll be just annoying if this happens really like, let's say 20 times in a row. The other reason is maybe the teacher is suboptimal, so you also want to like wean off. So I guess the nice intuitive example I like to give here is, let's say you're trying to learn how to play tennis and you want to be a grandmaster in tennis. You'll probably learn you from a coach initially, but after some point you want to probably learn on your own rather than relying on this coach, because maybe the coach is not as good as a grandmaster, but hopefully with your own learning you can figure out how to get there. So this is also the intuition here, that you probably want to sort of outperform the teacher, but also you don't want to keep track of the past teachers if you do this multiple times, or do reincarnation multiple times. And I guess finally, this is sort of obvious. It should be compute and sample efficient, because there's really not much utility in reincarnation if it's not cheaper than training from scratch. So these are the 3 sort of desiderata, which is, it should be the reincarnating algorithm should be teacher agnostic. We should be able to wean off the teacher policy. And finally, it should be compute efficient if it has to be a useful algorithm. Okay, so I guess I will jump gears a little bit here. So I described to you about the setup. I'm not going to go into the details about what algorithms and whatnot. Like, assume a world where you have access to such a useful algorithm. Like, let's assume a world where you have access to this algorithm where you can go from a policy to a value-based agent. And I guess I'm going to show now what can you do if you had access to such a thing. So I'm going to use, I think, Atari as a benchmark again to showcase the utility of this sort of workflow for accelerating research in general. Okay, so I guess most people know about Atari, or the arcade learning environment. And I guess the agent which started research or spurred the research in deep reinforcement learning was NatureDQN back in, I think, 2013. So let's assume we have access to this agent. So this is what the slide is showing here, that let's say we have access to this NatureDQN agent trained by Mini et al. In 2015. And this is the most popular agent, presumably in deep reinforcement learning, let's say. Now, what are we going to see is we're going to see how past research on ALE could have been accelerated by incorporating a reincarnating RL approach to designing agent instead of always retraining agents from scratch. So I handed to you this like sort of DQN agent, and I think the performance here is shown here aggregated across, I think, 10 different games. All right. So this agent actually used used the RMS prop optimizer, but we know nowadays in deep learning that Adam is a more stable, or let's say usually more performant optimizer than RMS prop. So let's say we want to switch to Adam. So one thing you can do is you can totally just train a new DQN agent from scratch. And so that's what the red line here is showing. The axes on the first and the second panel are very different, but we know from, like, I guess, experiments that DQN Adam is a better agent than NatureDQN. So you can do this, but you can also just fine tune your existing NatureDQN agent. And we see that the fine tuning the existing agent significantly improves performance of this agent. You also see a huge sharp jump as soon as I started fine tuning, and that was because of reduced learning rate. So I just take an existing DQN nature agent and just started fine tuning with the reduced learning rate, and I see a huge jump in performance. This is also something we observe in supervised learning, so maybe it's related to that. But you can see that it clearly outperforms the NatureDQN agent. And now you can also just like use the nature DQN agent for fine tuning as opposed to fine tuning the same exact agent. So if I fine tune the nature DQN agent as opposed to training from scratch, I can actually match the performance of this nature DQN agent trained for 400 million frames, which is about a week of training in only a few hours of training. So you can see how much amount of compute and samples you really saved by fine tuning an existing agent here as opposed to training from scratch. Now, so far so good. Do people have any doubts or questions about what happened here? Because maybe I moved a little too fast.
What's the difference between the two fine-tune lines?
Oh, so the green line is using fine tuning with RMS prop or using the same agent for fine tuning, while the blue line is switching the optimizer from RMS prop to Adam. So the original agent was trained with RMS prop, but you don't have to fine tune with the same optimizer. The one difference, which, or at least one crucial bit here, was you have to reduce the learning rate when you're fine tuning. If you don't do that, then you don't see this huge gain in performance. Because if you look at the original agent, you see that it has almost saturated in performance with longer training. But the new agent shows like a huge jump in performance as soon as you start fine tuning. And we just found out because we were saying, oh, well, let's tune this learning rate also when doing this.
Let's see. So far, I think my question would be, are we supposed to be surprised by this? Of course, if you fine tune, it's going to be much better than starting from scratch.
Yeah, I guess the more interesting result here was that you can, so this is kind of, you can say that too. So one interesting bit here was you can reach the performance. If you were to train from scratch for a week, you can just reach the same performance if you were to fine tune with using only a few hours. And I guess it's not really surprising. It's an argument saying, so why are we not doing it? Because we're not really doing it.
Well, I think the reason why we're not doing it is a cleaner study, because right now we're not sure if Adam is better than RMS prop because we continue training. But the red line is if you train it in the same amount of time as the green would show you that, oh, okay, Adam should have been the one that we.
Yeah, so that's actually a fairly good point. And I think the counter to that is when you're training agents from scratch, you only know that these two agents, like one agent is better than the other agent if you were to train from scratch. But let's say if you were not to do this from scratch, which is often what happens in, let's say, a realistic setup where you already have some sort of existing agent or something to begin with. And now you ask, okay, is this algorithm better than this other algorithm? It's not clear because you only have results from scratch training. So, and I guess I'll also come back to this again when I talk about this. But here also, at least you can say DQ and Adam, or Adam is better than RMS prop, even for fine tuning, comparing the green and the blue line. You can't say that whether this is the case for scratch training for sure, but you can say something else. At least you can make a research conclusion still. Let me move forward, and I think this thing will again come when I talk about this more. Okay, so fine tuning is great, but fine tuning is actually pretty limited because you have to use possibly the same architecture and often the same algorithm. So we said let's now consider like a more general reincarnating RL approach to improve on fine tuning by leveraging both the architectural and algorithmic advances since DQN without the simple complexity of training from scratch. So here what we did was we switched from the DQN nature agent, which is a 3-layer convolutional neural network and almost a decade-old DQN algorithm, to a ResNet agent with the Rainbow algorithm, which is a much more advanced algorithm than DQN. And ResNet is way more bigger, or at least much more better architecture than the small 3-layer conv architecture we use. And you can see that you can train this agent from scratch, and it actually gets a huge performance. But you can also fine tune the existing DQN nature agent, DQN agent, and you see that it sort of has diminishing returns. But if you were to reincarnate the DQN agent and convert this to this Impala CNN Rainbow, or the ResNet Rainbow agent I just mentioned, you can see that you can outperform the tabula rasa agent throughout training. And basically, you get like save around 1 day of GPU training if you do this, as opposed to training from scratch. So you can try the change you wanted to make, which is you can just switch to another agent and compare it to basically fine tuning your existing agent or training that agent from scratch. So those are the comparisons you can make here. And you can see that there's a clear benefit of restarting, or at least reincarnating from the existing agent as opposed to training from scratch. And again, I'm just saying you can still do algorithmic comparisons and whatnot. The setup is different. You're not comparing algorithms trained from scratch. You're comparing algorithm given access to some computational work, but the computational work is same across all the agents. And this is what we anyways do in a lot of like NLP and vision tasks, where we really are not training things from scratch. Let's say I want to solve a specific NLP task. I'm not going there and just be like, hey, I'm going to solve this task from scratch. You probably try to build on an existing trained, let's say, language model, or for vision, maybe you're using ImageNet features to fine tune or something like that. While in RL, we're always training things from scratch. And I think this is what I'm making case for, that doesn't really have to be the case. We can also build on existing computational work such as agents. Okay. I don't know if people understood this figure, but I assume there are no questions, so they did. All right. So I guess I mentioned this setup before. Let me just go back to, so I guess there is this one thing which I didn't clarify, which is how am I actually reincarnating a DQN nature agent with a 3-layer architecture to a ResNet with a different algorithm rainbow, and how am I doing it? And this is what the arrows are trying to show. Like, there is a reincarnation thing happening from the blue line to the pink line. And I guess I earlier mentioned that assume you have access to a reasonable algorithm for reincarnation. And I guess this is what I'm going to talk about quickly now. So the setup we used to, was there a question?
Sometimes people in the chat box asking some questions. I don't know, somebody
I see.
gonna answer them or not, or at least somebody read or not.
I see. Okay, I guess maybe this is a good point to answer some chat questions. Okay, we'll go through them quickly and see downloading, blah, 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 blah. Okay. I don't understand this question of how many machine learning engineers does it take to.
We're trying to figure out the sound setting and sharing.
I see. Okay. So what's the difference? Yeah, I guess someone asked, what's the difference between reincarnating RL and transfer learning? That's actually a pretty good question. So you can think of, well, what we traditionally call transfer learning, in at least in RL, is you often focus on different tasks, which is you want to go from one task to another task. Here I'm saying, don't even worry about different tasks. Think of a single task you have, and you want to leverage prior computational work. So you can think of it as transfer learning on a single task, but I want to use prior, let's say, computation I've done. But I guess the other main difference is, basically transfer learning is not arguing for saying, hey, let's change how we do research itself. It's just, rather than saying I will just start training from scratch, I'm saying let's just build on, let's say, some existing computation, like the way people in NLP or vision do. So that's another crucial difference. But I guess if you want to think of the technical aspect, you can think of it as a transfer learning, where you are in a single task and you want to reuse prior computation. I see. Switch architecture. How do we switch architectures while fine tuning? Yeah, so this is what I'm going to talk about next. You're not, first of all, that's where the algorithmic development, and that's why you need something else, because fine tuning just doesn't work if you want to switch architectures. So this will be the next part of the talk. Hopefully that'll be answered there. Yeah, I think someone else also answered that. Cool. Okay. So let me talk about how did I manage to do going from a DQ and Adam agent to an Impala CNN Rainbow, which is a different architecture and also a much more complicated and advanced algorithm. Right. So for this, I guess I'm going to talk about this experimental setup which we used to benchmark different algorithms. So what we did here was we took like a DQ agent trained for 400 million frames, which is around 7 days on a single GPU. And we also assume access to the replay buffer of this agent, which we have anyways. And what we want to do is we want to transfer this to another student DQN agent using only 10 million frames, which is around, like, I think 40 times smaller than what the original teacher agent was trained for. And for this, we used 10 parry games with key actions. And for evaluation, we used interquartile mean, which is like similar to the reasonable metric. Okay. And so there's not really existing approaches which work for the PVRL setting based on the, I think, the desiderata, if you remember, I described earlier, which is it has to be teacher agnostic, meaning of teacher computer efficient. But there are a lot of closely related methods which we can adapt for this setup. So what we did that. So we adapted like a few of these methods from like continual learning, or even like RL literature from offline RL, or even things like, I guess, learning from demonstrations and whatnot. So a few approaches I'm going to list here is like, first of them we tried was rehearsal, which is if you have a teacher policy, you can just replay samples from that teacher policy. If you have some data, which is we have access to the replay buffer selected by the teacher agent, we can just do some pre-training on that data with offline RL and then fine tune. You can also do something called kickstarting, which is it's basically a combination of Q learning and distillation, except one main difference from supervised learning is that your student is collecting the data. and the teacher is just giving it labels to correct on that data. Or think of it as like you do something, you ask the teacher, hey, did I do it well? And the teacher tells you whether you did well or not. So you do some combination of Q learning plus this. DQFT is a very popular approach for learning from demonstrations. And I guess JSRL is another work called Jumpstarting RL, which focuses on using, or at least collecting data using this teacher policy smartly. And I guess just going to quickly flash the results. So in the setup we said was like we have a teacher agent trained for 400 million frames, and we're going to train another policy for 10 million frames. We see that most of these existing methods are not even able to surpass or even match the performance of my teacher policy in 10 million frames. Look at the left plot, and you can also see that Q-dagger, I guess, which is the algorithm we propose as a baseline for sort of this sort of setup, is able to do reasonably well. And if you look at the right panel, what I'm showing is the distribution of scores across all the tasks. So here I have, I think, 10 tasks and 3 runs. So it's the distribution scores across all the 30 runs. And you can see that if you read the vertical line, so basically the y-axis is showing fraction of runs on which you score higher than a certain threshold or certain value. So if you draw a line at 1, you can see that Q-dagger is able to outperform the teacher in around 75% of the runs, because that's where the vertical line intersects the plot, the blue plot. But basically, the right-hand side plot is a distribution plot. This is just like a tail distribution plot, while the left-hand side plot is an aggregate performance plot. So you can just read the left one, right one is harder to read. But overall, the takeaway is existing methods are really sort of not that good. And especially, you'll also see some collapse happening. If you look at, for example, the light green line. But existing methods are not good, and there are like basically challenges you have to tackle, and there might be scope for further improvement. And just to quickly describe what Q-dagger is doing, it's really like a simple baseline. I don't think it's an advanced method, and possibly you can do much better than what we are doing here. So what it does is it combines Q-learning with Dagger, and Dagger is a really popular imitation learning algorithm. So what we do is initially you pre-train on teacher collected data, which is you just combine these two, imitation learning and this Q-learning loss, but on offline data. And then you train on your own collected data. And you can also see there's this bit about weaning off the teacher, which is we wean off the supervised learning loss as we train more in the online RL setting, because you want to eventually be independent of this teacher. And also the teacher is suboptimal, so you don't really want to copy what the teacher does, because possibly you can improve on this. And I think I'll show an ablation how important this is later in the slides. I'm already at 40 minutes, I guess, being cognizant of time, so it should be good, I think. Okay, so we ran it on a difficult humanoid task too, but I think I'll skip it because of time. Let me show you what was the motivation of this project. So I think in the Montreal team here, which I'm a part of, some researchers trained an agent with distributed reinforcement learning for more than a month, which can fly balloons in the atmosphere. And this was actually deployed in the real world. So DeepRL was actually able to fly balloons in the atmosphere. And this is a really hard problem because you have to basically navigate the winds. And this is what the animation here is showing, that basically winds are flowing and your balloon has 3 actions: move up, move down, or stay. And it has to just navigate with the wind so that it stays in the circle you see at the bottom. So it has to stay within that circle. So it's a really hard problem actually. And before DeepRL was applied here, people were using some handcrafted controllers with like a big team of engineers building that controller. Now, we already have access to this agent, and I think we can ask this question of how can we improve on this agent? Now, you can train another agent for another month maybe to do this, but that just seems like an overkill and maybe just like not feasible. So what if we set up this problem of, okay, I give you like a finite amount of compute, which is, I think here it was 10 to 12 hours on a TPU V2, which will cost you around $50 if you were to go now and like get this much compute. And we asked like, how much progress can we make if we were to do this? And we find that you can train agents tabula rasa, which is the first 3 lines, or you can use reincarnation to improve on the existing teacher policy, or you can fine tune the existing one. And I guess we saw that the reincarnated agents or the fine tuning ones were really doing much better than tabula rasa. One catch here was so reincarnation, or at least transferring to a different agent altogether, was not still as strong as fine-tuning the existing agent. And part of the reason was that the existing agent was trained in a much more richer simulator, while the one we are training on right now is a less diverse simulator. And because of that, I guess we expect that maybe we were not able to transfer the entire information when we were doing reincarnation with our method. So I think the the worst performance of reincarnation compared to fine-tuning is more or less because of we are not able to transfer fully the information which is in the weights of the existing agents. And if we do a better job at that, maybe you'll see much better performance. Other than that, you can see that basically we're able to do much better than basically training agents from scratch within that finite amount of compute. So now even like researchers outside possibly Google can take this existing agent and build on that, as opposed to, let's say, training an agent for like multiple days to make progress on this sort of problem. All right, hopefully there are no questions yet. I didn't see anything in chat also. I guess someone asks, what are sticky actions? So sticky actions are basically just a way to induce stochasticity in your environment. So here, I think in entirety, it means that each time you take an action, there's a 25% probability that some random action is taken instead of that action, and it just makes the problem difficult. So that you don't overfit to the deterministic nature of this environment. All right. So I'm just going to quickly show what are some considerations. So I think I presented this result about fine-tuning and reduced learning rate. And this is maybe something which people who do supervised learning may not find surprising at all. At least for RL folks, it was a little bit interesting and surprising that we found that if you take an existing agent and just keep fine-tuning it with the same learning rate, it actually wouldn't show any improvement in performance. But if we simply just reduce the learning rate by a factor of 5 and fine-tune it, we see a massive improvement in performance. I think we see around like 50% improvement for one of the agents and 25% improvement for another agent. So, but more interestingly, because I think as Reincarnating RL focus on leveraging existing computational work, it allows us to easily experiment with such hyperparameter changes, which is really expensive in the tabula rasa setting, because I took an agent trained for 200 million frames and then tried this hyperparameter change. If you were to experiment this from scratch, it will become a really expensive hyperparameter change. So yeah, so that's one of the nice aspects. Because we're focusing on reusing existing stuff, some of these experiments become really easy to try. The second thing is about, I guess, how is it different from just distillation, which is I mentioned about this thing about weaning off the teacher. And here I think you can clearly see. So what I'm doing here is running two ablations of the Q-dagger method I presented. So you can just do pure imitation learning, which is the green line or dagger, or you can do a combination of imitation learning and reinforcement learning, which is dagger plus Q learning. And versus the Q-dagger method, which weans off the teacher, basically just pure reinforcement learning as soon as it thinks that it's as good as the teacher. And you can see that Q-dagger significantly outperforms doing just imitation learning or combining imitation learning and reinforcement learning throughout training. So basically, this also shows that what is the benefit of weaning off the teacher, because the teacher gets a performance around 1. And if you always try to distill the teacher, then maybe you'll just saturate around that performance. But if you were to, let's say, move away from this teacher, maybe you can see a lot more gains because the agent can learn a lot from its self-collected data. I guess one thing is that in the performance in Reincarnating RL is dependent on existing computational work. So I guess in the setup I presented, it's dependent on teacher policies. And this is pretty similar to machine learning areas such as, let's say, NLP and vision, where building upon pre-trained models is the dominant paradigm, and the results you get are going to be dependent on what pre-trained model you use. For example, let's say if you use BERT as a pre-trained model, or let's say these days maybe use something like GPT-3 or some transformer-based model. So the results will be dependent on that. But we still do these things in NLP and vision. And I guess that shouldn't stop us in RL to do these things. And what I'm showing here in the slide is basically I'm taking like 3 different existing trained policies and showing how we can do reincarnation on top of them. And 2 of the policies were obtained through very different ways, and they have very different behaviors. They just end up with different performance. And you can see that if I reincarnate a student agent, so look at the yellow and the green line, if you reincarnate 2 student agents using these 2 policies, you see different performances. And the reason is that even though these 2 teacher policies have the same performance, they have very different behaviors. And that's why we see different sort of behaviors in the student also. So basically the performance you get will be dependent on the teacher policy you have. But I guess the hope or expectation is that the ranking or the findings would be about how good an algorithm is given access to a prior computational work. And we see that the ranking of algorithms still doesn't change and it remains the same. So still here it's the case that the top 3 best algorithms we had in like using one of these teacher policies, the same if you were to switch the teacher policy. So this is what research in this area would look like, which is you take on some existing computational work, fix it, and then just use it for all your algorithmic comparisons. And hopefully this existing computational work is also standardized. Like researchers decide on, okay, let's just use this model, like the way in NLP and vision, everyone says, okay, let's just use GPT-3 or GPT-2 or whatever, some standardized model to build on. And finally, I guess coming back to Roseanne's question about cleaner versus not cleaner. So when we are comparing RL agents, I guess we are always focusing on whether this RL agent is good when we are training from scratch. But that can be misleading if we want to ask the question of, okay, is this RL agent good when we are starting from some existing computational work? Or even the question of, is this RL agent good asymptotically compared to another agent? So here what I'm showing is I took two agents, I think DRQ and Rainbow. And you can see that DRQ is much better than Rainbow in the, basically, if you train from scratch until 10 million frames, and after that Rainbow takes over compared to DRQ. But if you were to compare the same algorithms in the reincarnating RL setting, where now they correspond to the green and yellow line, you see an immediate flip in ranking, which is Rainbow is always better than this DRQ algorithm. And this matches more like the asymptotic ranking we get with these two algorithms, but doesn't really match the tabula rasa ranking we get if we were to train these agents for a small amount of frames. So I guess basically what we are saying is there's a possibility that we can develop better student agents that can utilize existing prior computational work, but they may not be better for tabula rasa, and vice versa. That if we have a better tabula rasa algorithm, it's possible that it's not better for like reusing prior computation. And I guess that's why it's important to study this sort of problem setting also, in addition to just, let's say, doing tabula rasa. I guess that was the last result on my slide. And finally, I guess I'd like to say, this is a quote from Newton saying, if I've seen it further, it is by standing upon the shoulder of giants. And here we are literally saying, let's just not stand on ideas, but also on the computation people do. Okay, I see some questions. I guess people can just ask questions because it's people are posted in chat. I can see one. So someone says, to summarize the Q-dagger approach, have a pre-trained model on the same problem, start your agent from scratch using Q-learning and decade input from the pre-trained model, that's it. No, actually, that's pretty far from what Q-dagger is. So maybe I didn't explain it that well. But basically, you start from a pre-trained model, and now you want to start another model or another agent, which could be totally different from this pre-trained model. And what you do is you first train on the data collected by your pre-trained model, which is often presented to you in reinforcement learning as a replay buffer or something like that. So you do Q-learning and some sort of imitation learning or distillation loss on this data. And then you train your online model, or at least the new model you created, a new agent you created, in a reinforcement learning context. So I think one difference may be in reinforcement learning, in supervised learning, we don't really have like fixed use data sets. So when I say training from scratch, really just an agent is started in an environment without any prior interactions. And here I'm saying, hey, what if I gave you an existing policy also? So what do you do with it? So you start with just imitating that policy and doing RL, and then forget about imitating over time and just do pure RL. Do you ever find pre-trained policies to get too stuck in the way that didn't allow for behavior you wanted to emerge? That's actually a really good question. So it depends on how strongly and what method you use to leverage the existing policy. So I think Robin is asking, let's say if I gave you a really, let's say, policy which is too stuck in doing something specific, and maybe you can't really improve on it. So what do? Maybe you just overfit to what this policy is doing. It is possible, but the assumption is that we are like basically we're assuming that this policy is suboptimal to begin with, and how we use it should govern how much we overfit. So for example, even for the method I presented, if I do too much of distillation or imitation, that actually hurts eventually in the RL phase, because maybe I just overfitted to this existing policy. So that parameter, I guess I can quickly go back to the slide where this parameter was. So yeah, this distillation parameter, lambda t, this actually is an important coefficient. If you, let's say, set it too high, basically you end up just overfitting to the existing policy and not improve too much. So you have to make sure that you don't really like focus on too much transferring. The downside is if you set it too low, then maybe you'll not transfer it as much and it'll be not as efficient. So that's why I think there might be scope for much better algorithms here. But again, the assumption is, you know that you have access to some suboptimal computation. How do you use it? That's the problem we're presenting. And I'm saying I really don't know what's the good algorithm for this. I'm presenting one, but there might be much better out there. And this is just really a start here.
So I have a question. So not a question, more of a comment. I feel like the reincarnating compared to fine tuning, one advantage is you just need the policy. You don't need to access the model weights.
Yeah, so that's the other thing. So fine tuning is probably, well, the thing is often fine tuning is possible, but so there are two issues with fine tuning. You also have to use the same architecture often, but for reincarnating, we're saying do whatever, we don't care. We are just saying we gave you a policy, how do you use this? So that's the nice thing. The downside of reincarnation is, so when you just reuse the model weights, you get like the policy for free. You don't have to do any sort of learning to recover this policy again. While when you're focusing on transferring, there is a cost of transfer, which is you have to maybe collect some new data or you have to train on some existing data. So reincarnation has a cost while fine tuning doesn't, but then reincarnation comes with more flexibility. So there are like merits and downsides of both. And I think that fine tuning has been popular traditionally because if you really start from a huge model, you can't really do much other than fine tuning. But if you were to, let's say, transfer it to a smaller agent or something like that, then it might again open up ways of using this big model in more interesting ways. And I guess maybe one general comment. So I mentioned this all about RL, but even if you think of NLP or other domains, so let's say you trained a big model after, let's say, training on a cluster for a year or so, and now you want to train another better model. It is weird that we throw away all of this computation and just train another model for another year. So it's possible that this sort of setup is also meaningful in just like NLP or Vision 2. But in RL, it makes a lot more sense because we also don't have access to existing data or the data which we use for training. Like we don't have supervised data. We want to recover this agent's performance again without using that supervised data because we don't have it.
Yeah, and I'm also thinking of a future scenario where, because all these work, fine-tuning or reincarnating, rely on other people releasing their model. Maybe for future work, people would release their model, but don't want to release all the weights for security reasons. If we can only get to infer the model and the policy, and we can do something with that, that will be a huge advantage.
Yeah, that is actually a good point. I didn't think about it. But yeah, you only need access to inference, or at least like get access to the policy for reincarnation. For fine tuning, you need access to the weights. The other, I guess, this is also an interesting thing. We are implicitly arguing here that we want people to basically release their computational work in addition to their paper, because if they do it, maybe it'll allow others to build on their work easily and do things like, let's say I take in a tardy agent and do something quickly on top of it and get like reasonable performance, even match state of the art performance, but with like a fraction of the compute. So let others do interesting research without having to do like computationally expensive stuff.
Also, I find it interesting that you can switch from a policy-based network to a value-based training. And I wonder if this will change the whole training paradigm where people would find out, oh, you can just do different phases. You should get back to policy-based. It's like reincarnating many times actually is the way to train RL or something.
Yeah, so that was actually a not so easy problem to do, like going from policy to value-based. And I guess there are more interesting things or more weird things you may want to think of. Let's say if I go from a policy to a model-based or even more vacui things, I couldn't imagine right now. But basically, that was not trivial. And the reason it was not trivial was because no one has actually tried to do it before. People have focused mostly on policy to policy, but as soon as you introduce this value, suddenly it becomes more complicated. And that's what the pitch here was saying, hey, maybe this problem is also worthwhile studying, or at least all of researchers don't have to do tabula rasa or specific problem setups. The hope is actually people do I don't know what it means for reproducibility, given that the last work we did was about reproducibility. If really just people went like, oh, I'll use your agent and someone else uses their agent and so on and so forth, it would, I think reproducibility would start meaning different things, or at least reproducibility from scratch would not be a thing anymore. It would be more about, hey, given access to certain computation, I can reproduce this work, but that's about it. I can't imagine reproducing the computation. Like the same way, if no one goes and be like, I'll try to retrain GPT-3, they just use what is given to them and build on top of that. I think we're running out of time.
I just want to make a comment. Before ending this session, I just want to get some recommendation within 1 or 2 minutes. I don't want to ask for another session with you personally. And then let me know when it is and get some recommendation. Thank you.
Wait, you wanted some recommendations about?
Yeah. When it's the end of this meeting, and
I see.
in the end-
Okay. Okay, sure. Yeah, I have a few minutes.
I guess it's the end of the session, or it's gonna be continued.
I think it is end of the session almost. You can maybe stop the recording, Roseanne.
Okay.
Thank you.